Yeah, yes, I can see the slides now.
Okay, cool. So, so the main thing that we are looking at here, and we discussed all the background behind it, is lazy code motion. And so the idea is to really start with placements which cover a particular expression along which it is not available, and try to cover it as early as possible, so that we don't introduce partial redundancy just by going to maybe the predecessor of the node and so on. And from there, the idea is to really get to the earliest point, try doing that coverage. And the other constraint that we are looking at is we are not going to place this in any path along which it was never originally going to get executed. So because if we place it, then it will increase the execution of that path. So those are the criterion for PRE, and that's what we'll be doing here in this particular exploration. And let me now go into some details of how that works. So as you know, we had looked at the PRE's formulation here, which is in the paper that we have given you, which is called as lazy code motion. That is, the placement of this expression should be as late as possible. And the PRE problem has been worked on for a while, but you can see that finally in 1993, which is sort of the Dreckler and Stradell paper, is easier understanding of this PRE framework. And the problem was in terms of lazy code motion was solved by Knoop in 93. So the idea here is to place this expression as late as possible because we don't want to hold the value of this expression for too long. So that is basically what we are going to see. And then now let me go and explain the the frameworks, which are very intuitive. And then we'll explain it in terms of how it really works. So PRE is a problem which is again very similar to, as you know, common sub-expression elimination. That is, we are eliminating an expression based on the lexical identity, first of all, not based on the value identity. So in other words, x plus y is the expression which we are trying to eliminate, and it has to be identical in terms of its operands and operator to the expression which we are getting rid of. So we can't eliminate p plus q using x plus y. That particular type of elimination is also possible for redundancy, and that particular problem is called as value related redundancy, that both have the exact same values. And to capture that is a little difficult problem than the notion of lexical identity or lexical equivalence of the expressions. The availability framework that we have defines the identity in terms of the lexical identity, but not in terms of value identity. It doesn't capture a plus b and x plus y as identical. So, so the analysis for available expressions is what we'll start with. which is the same as it's a forward analysis in terms of which expression is available where. And then once we have this analysis, we will also know the partial redundancy or partial availability of an expression, that the expression is not available along certain at certain basic blocks, along certain edges, and that will be of importance to us. So that analysis is a forward analysis. We'll find out about the availability and more importantly about non-availability of an expression, and use that to decide where the expression needs coverage. And then we'll try to the earliest points which will offer the coverage of the expression along the edges. And the second part of it, which is really about not lengthening the path, we will be worrying about the concept of anticipatability. And the anticipatability is tells us that if an expression is anticipatable at a given point, then what is the definition? The definition is same as very busy expression that we have seen. So what is the very busy expression? So the anticipatable expression or very busy expression tells us that we are at a given static program point, and if we traverse in any direction from there along any path, we will be meeting evaluation of an expression before any of the operands are redefined or before the program terminates. So if we go along a particular path, from that point we will see x plus y. Along another path we will see x plus y. No matter which way we go, we'll see x plus y being evaluated there. So anticipatability tells us that along all those paths that we are encountering, the expression is really evaluated. So basically it tells us that the expression's evaluation is there, and by inserting an by looking at that particular program point, we know that the expression's evaluation is there. Now let us, just like non-availability, let's look at non-anticipatability. Okay, so what does non-anticipatability tells us? Suppose an expression is not anticipatable at a given point or on a given edge. What it means is if we traverse from that edge or from that point, there is at least some path along which the expression was never ever evaluated in the original program. Otherwise it would have remained anticipatable there or very busy there. Now what is the implication of that? And the implication of that is if we go to an edge or a basic block along which the expression was non-anticipatable, then we are, and if we put that expression over there, then what is the effect of this? There might be a path at runtime along which the expression was never ever evaluated in the first place because it's not anticipatable there. And so by placement of such expression on a non-anticipatable point, we are going to elaborate the execution of the expression, elongate the path or put some superfluous expression at its execution. So that's the concept of anticipatability. So so let's kind of maybe illustrate these concepts here, which I talked about availability. So here is a basic block, and I hope you can see it, right? Nathan, can you see it?
Yes, I can see your drawing.
Okay. So here is my expression x plus y, which is available along this particular path and is not available along this path. Okay, so let's just call it not available with this bar. that x plus y was not available here. And so we need to cover this expression over here along this edge. We need to cover where I put a check mark there. Now, if we go back from there, then what may happen is we may have a situation like this. So if we try and place this expression here over where I put a circle, we could still be problematic because although it is not available, it could be partially available in the previous basic block. How? It could be that, maybe on this edge, x plus y was available, which I'm putting on the leftmost side. And on the other side, it was not available again. Now, if you place it at the circle point, you can see that this x plus y, which is available on the leftmost edge, would have come in here and would have made this the newly inserted x plus y in the circle redundant. And so partial redundancy is not solved here because whatever was partially redundant here, you just moved the problem of partial redundancy one level up because you are still suffering from it being available on one side and not being available on the other side. So what do you need to do here? You need to now not really place it here, but maybe place it along this edge, which I'm indicating at the top, because that's where if I place it, and it was not really evaluated on this side before, it's not even partially redundant here, so it was never even evaluated there when coming on the right hand side edge. So if I place it over here where I put this circle here, then if I put a x plus y here, you can see that it will not be partially redundant here because it was never ever evaluated. It was and then it will cover this x plus y, make it available here and make it available here also, and it will not introduce any redundancy. So this edge where we are, which I've drawn this arrow, which we call as earliest edge of placement. So how do we determine that? That's the question, without introducing the redundancy. Okay, so that is how we will try to move up in terms of non-availability. So what we'll do is we'll start wherever it is not available. We'll move along the path of non-availability. So we'll try and see if this is an earliest edge, and we will determine that is not an earliest edge based on certain criterion. And if we can move up, we'll try to move up, and then we'll determine this earliest edge, and I will explain you how the earliest edge is formally defined. And we'll sweep as early as possible. That way we will be placing that expression over there for the coverage. And then from that edge, we will determine how to, and we could have just settled down on that edge and we would have been done with the PRE problem. But in the LCM formulation, what it tells is don't just stop at the earliest edges of coverage of the expression. So let's say what would happen here, I'm just drawing it in the bottom, is let's say the expression is determined to be earliest at these two edges. For whatever reasons, we cannot move this above this for the coverage because if we try moving it above, it will of course generate a different value because x or y would have changed. In the predecessor basic block, like here, x or y would have changed. Maybe that could be one reason. Or if we could move above this particular point, then you can see that on the this basic block, number one, which I wrote here, if we try and move it into the basic block 1, then what is going to happen is now you have another path coming out of that basic block here, which is what I have shown. And on that path, if it was not anticipatable, that means originally along that path there was somewhere there was no evaluation of x plus y, and so if we place x plus y here or above that particular point, it is adding additional execution time over here, and so that's why this is not a right edge to place it on. So let's say that that's how the earliest points here are determined by these two circles, because if you cannot move above them in terms of redundancy removal under this definition of the problem, and so we can see that we could have just put the expression here and here, and we could have covered the expression. We would have, it's now become available here and becomes available along this particular path down here, and eventually it becomes available along the so we have gone along this path of non-availability from here backwards here, and now we have covered that particular path by coming in terms of covering the availability on this side, and we therefore covered it here on this side. Let's say the expression was already available. We just went along the path, determine the earliest edges of non-availability, place the expression at the earliest edge of non-availability, and we are done. And that way, now the expression is available here, and whatever redundancy we had, so let's say this one had an x plus y, we have eliminated that now because there is a x plus y here, there is a x plus y here, and that has made it available here all the way. This was already available on this side, and so we got rid of this redundancy, and this was the placement which would have solved the PRE problem. But as per LCM, lazy code motion, which is the formulation which we are interested in, we don't want to put it at the earliest points and just settle down there. What we want to do is push this expression as late as possible in terms of covering the non-availability. So let us say what will happen in this particular case. So if we leave it at that, it will not be a type of a solution. It will be a correct solution for partial redundancy removal, but it will not be the lazy code motion, because what we'll have to do is we'll have to hold the value of the expression here, value of the expression here in the register, and all the way along these paths, make it then available over here. So it will be a very long path along which we would have to hold the value of the expression, and so that's why it will not be the right solution as far as LCM is concerned. So what does LCM ask us to do? LCM asks us to postpone the evaluation of the expression as late as possible, so that partial redundancy is not violated, but we don't have to hold it for this long a path. So now let me modify this example here and show you what that means. So let's say that the expression originally, the reason why we could not place this expression right on the predecessor here, the circle edge, was that of course it was partially available here. Okay, it was partially available, and let's say this means that it was partially available here. That's the reason, and it was not available here along the right hand side path, and that's why we ended up doing x plus y at the top. Now in terms of covering the availability, we could have left it at the earliest positions, But LCM wise, what it tells us is push this x plus y as late as possible so that it doesn't come in the path of availability. So you can see that the correct place at which we should be hosting this expression is where I just drew the circle. So this particular circle, which I just drew, you can see that we can sink this x plus y over here all the way to this point, which I call as 1. And if we push it any later, like here, for example, in the basic block that is below it, it is going to create problems because this expression now comes in the path of availability. So this was available along this edge, and if we put it here, then it will become partially redundant again. So we will make sure that we stop at this point where it joins the availability edge on left-hand side, and we will place it at this edge. So now you can see that instead of placing it at the earliest, we'll place it at the point 1, wherein it will cover the non-availability on the right-hand side of the path, and the availability, it will join with the availability on the left-hand side, making it available here in this basic block and therefore available here. So that is exactly what what I summarized just now is really what is PRE framework. So what we do is, in short, start at the point where the partial redundancy is there. We go back and examine an edge if it is earliest. Why do we do earliest thing? Because if we don't, then we'll end up looking at this point where the lowest circle is. And if we place it there, then we'll be in the path of non-availability. But that path of non-availability could mean that it is still available along this particular circled edge at the top. And it would lead to partial redundancy still being present, but now just shifted to the edge. So that is why we keep sweeping backwards, and we keep going along this path, which is going on the right hand side all the way at the top, and we'll stop there. Why can't we sweep above that particular path? Because one of the two things happens there. Either the condition of keeping the expression's value intact is violated. So if we go above this point in this block, let's say x was redefined, because of which we can't go above that part, because if we go above that part, then the value of x plus y will be changing. So that is a stopping condition. Which are the definition points? The expression has to be kept only after the last definition point. So that stops going above that. So that's why it defines an earliest edge with regard to coverage using the same value of x plus y as it would exist at the original point. And second condition is that we don't have x or y being redefined, but it's simply that if we try to push through that block above, we are coming in the path of anticipatability or non-anticipatability. What it means is an expression is originally is not being evaluated along at least one of the paths. And so if you show it into the basic block 1 here, which is shown on the left hand side, then originally there was no such evaluation of this expression along at least one path from which originates at that point. Now, if that path is taken, you can see that x plus y will become superfluous in terms of its evaluation, and therefore will lead to execution of unnecessary more amount of code, and that's why we can't move it above that point 1. So that was the stopping condition, and and from there we decided to push it down from the earliest points by using lazy code motion to a latest point. What is the latest point? The latest point is 1 below which it will meet availability, coming along at least one of the edges. Like over here, this particular availability where I just draw an arrow or a check mark, if you sink it below here, it is going to meet this availability, and that is going to create redundancy again, and so that's where we simply stop. Okay. um, why couldn't we come up with number one just begin with? We could not come up with that because we didn't know anything about the availability or partial availability, whether it exists above this particular point or not. Only when we swept above this, we knew that there was no availability on this edge and there was no availability along that edge, and that's why we covered it. If there were availability along one of the edges, we would not place it there. We will simply place it on the other edge. So for example, if there was availability along just this arrow below 1, the expression was available, we will not place it there. We would have placed it on the x plus y on the right hand side where I just draw a circle. And in that case, when we start sinking, that would be the position at which we will leave it. We will not sink below it because then it would meet the availability again on the left hand side. And that's why that would be the final place for placement of x plus y. Now, so that's the overall framework, how the points are determined through a backward sweep first, and then to implement LCM, a forward sweep is carried out, push down is carried out till the point of meeting the path of availability and stopping just short of it on the incoming edge. Now, you may ask me, does partial redundancy still remain in place because of this? And the answer to that is yes. And you can see here, just focus on these two stopping conditions for earliestness. So on the right hand side, we stopped on that edge because there was a redefinition of x or y here at this particular block, and we couldn't have gone up anywhere above this. And so this is a case of course, holding the expression x plus y here because it does generate a new value and it's completely needed for the coverage. But look at the left hand side, x plus y, just before the block 1 here. What is going on? We could not go above that particular point because of what? Because of the non-anticipatability. It's not anticipatable above that point. Does it mean that it is not available? It doesn't mean that at all. So in short, it could be that this new arrow which I have drawn here, and I call this as 2, number 2 point, it was available along this particular path, okay, coming in. And we would have liked to sweep this expression over basic block 1 above and avoid this 2's path completely and place it on the right hand side of this. But we could not do so because crossing this block 1 and going above would violate the anticipatability condition, and we could not do that because it will introduce an expression in a path where it is superfluous. So if we, for example, go on this path, the right hand side top of block 1, we can't do it because the moment we cross above 1 in anywhere, including one of the incoming edges, we would be if we take this path, which starts at the right hand top edge and go through 1 and go to the left hand bottom where that cross is, along which there was no evaluation of expression. Now you can see that that path is elongated, or there is a superfluous evaluation there, and that is why we can't go above 1. And so that's why we had to stop below 1 on the right hand side. Now what is the implication? The implication is this, that partial redundancy does remain there. How? Because x plus y is available on 2, and if we cross 1 using that value and go on that edge x plus y, which is at the bottom right side, then we have x plus y evaluating twice, and that's the case of redundancy. But that is inevitable given the definition of the problem. This amount of redundancy has to remain if your condition stipulates that you cannot introduce elongation of path, which is a correct condition. So you have to live with that solution. That's the solution which is, so there is no solution possible to the problem in which you have zero partial redundancy and you have absolutely no um, um, elongation of path. It is simply impossible for this example to do so. So you leave it with the remnant partial redundancy which is there because of this condition. Now, is this explanation clear in terms of understanding of partial redundancy we're doing? Let me again repeat the overall solution. We start from a point of where the partial redundancy is. We visit the predecessor edges of that basic block, and we find out the edge where there is no availability or availability is not true. So for example, in this case, we'll leave out the right-hand side edge, which is the right checkpoint because there is a availability. We'll go to the left-hand side. But we will not stop there. We will visit the predecessor block of that edge, and we will verify if this particular edge is the earliest edge. What is an earliest edge? Earliest edge means we cannot go above this particular edge in terms of placement of expression. And if it is not an earliest edge, which is what is shown here, we'll keep moving through that block along the edge where things are not available. We'll leave out the edge where things are available. We don't do anything to them because the expression is there already. We don't need to cover it. The whole idea here is to find out the points of where we must place it for coverage. So we'll go on the top basic block here and then go to its right hand edge and then go to its predecessors and its predecessor edges and so on. And that's where we'll find out if we are at the earliest edge. How do we know we are at the earliest edge? Because we can't go above that on the predecessor basic block because of the redefinition of the operand. And in the other case, we can't go above that edge in terms of introducing an extra computation or what we call as violation of non-anticipatability. And so that is where we place this expression for coverage on non-availability side. And from there, we'll try syncing it unless and until we will meet the path of availability, such as in this case shown here, and place it at number 1 because this is available along this side and it is not available along this side, and so we can't sync below it, and that's where we'll place it and we'll be done. And then we'll delete this because of based on this. So that's one mode of operation for syncing side. Let me quickly talk about the second mode of syncing, where we need to stop. So this stoppage in terms of meeting of a non-availability edge, like in this condition, is one mode, but the other mode could be at the top. So let's say we started with the placement of x plus y on left-hand side and x plus y on the right-hand side at the earliest edges. But what if in this block where I'm pointing to, we have an original evaluation of x plus y? So then what do we do? So we now have a need to cover an expression because there is an evaluation point of x plus y in this one. And so there is a need to cover that expression in that block. And so when that is the case, we will stop at the current edges over here, place the x plus y here, place the x plus y here, and we'll try to sync in the x plus y through these edges and find out if that is the creates redundancy, and we'll get rid of this x plus y over there because you can see that as far as that x plus y is concerned, its need for coverage. We started with placement on the both of these earlier stages, which are right at its predecessors. And from there we sunk it down because it was not available on both sides. We sunk it down, and that means that this was an expression which is sort of uppermost evaluation of x plus y, which should be left intact, and we don't need to cover it by using right hand side x plus y and left hand side x plus y. In short, the non-availability here means it is completely not available on any of the edges, in short. That's what basically the implication was, and such expressions are left intact there. And from there, of course, x plus y will become available, and it will cover this example. It would have covered all the original expression also here, and so no other placement would have been done here. The original x plus y here would be left intact. So in short, what it means is this PRE formulation also covers the case of CAC, and leaving those CAC solutions intact, which are the uppermost expressions which generate the total redundancy. They will leave those intact. So in that sense, the CAC problem is also being solved by the PRE problem, and also the lazy code motion, as I mentioned. These two are sort of the implications of this. So are there any questions about these? Otherwise, we'll look at the formal framework. I'll take a pause here and ask if there are any questions. No questions?
No questions in chat.
Okay. All right. So it looks like this framework is not very difficult to understand given what I said. So let's go through the formal ways then. So here are analyses then which are at the heart of PRE. So we are just finding availability and anticipatability in one is forward directional data flow, and second is backward. So the forward direction, downward exposed expressions, which means the expressions which get defined in a basic block and which survive to the end of the block because of no redefinition. So that is basically the starting point of availability, because those expressions then become available from the point of their evaluation. So downward exposed expression here are the locally defined expressions in the basic block which define availability, and upward exposed expressions define the anticipatability or very busyness. So what are those expressions? The ones which are evaluated towards the beginning of the basic block and have no operands which are redefined from the beginning of the basic block till the evaluation point of expression. Those are upward exposed. So those expressions, which means that if we can move them to the beginning of the basic, the same value in short, and that defines the anticipatability or the very busyness. We'll use the word anticipatability here because that's the definition which is used by PRE formulations. So this is the starting point of analysis to determine the upward exposed expressions which define anticipatability, downward exposed which define the availability. And then we have the set of sense of killed expression in a basic block. One of the operands is redefined, and so basically this expression doesn't survive the downward motion through the block, which is meant for availability, or upward, which is meant for anticipatability. Once you cross the evaluation point, once you cross this redefinition point, either in upward direction, it no longer is anticipatable, and in the downward direction is no longer available. Okay, so these are now we propagate this information, and it's the same exact framework which is we use for available expressions, just define written in slightly different notation. So when do we say a particular expression is available at a given point? We say it is available when it is available along all paths that are coming into that point. So along each edge, it should be available. It should be evaluated, and that value which is evaluated should remain intact after the evaluation point. So no redefinition allowed for downward exposed. And then it should be available along all incoming edges, and that's why the intersection there. And then within a block, the translation of an expression is this. If it's downward exposed, then it becomes available in that block at the output. Otherwise, the second possibility is it is available in the input of the block, and it is not killed. So you can see that it just nicely passes through and it remains available. Okay, exact same definitions. It's written in a slightly different form in terms of operators. Rather than subtracting the set of killed expressions, it's just you take an intersection with the negation of the set. So that's all the difference is. But the sets and the definitions and what they produce remains exactly same. So these are the sets of available expressions which we find out at the beginning on the end of each of the basic blocks. So anticipatability. So the anticipatability is again the sense of that we are at a given program point. And what is the definition of anticipatability? Anticipatability tells us that no matter which way we go, we will meet an evaluation point of x plus y before we meet any redefinition that operands, or we terminate the program. So which basically means that on every path there is an evaluation of x plus y that we meet. So that is captured very simply in a backward analysis, just similar to the very busy expressions. Anticipatable at a given point means at the beginning of the basic block. Let's look at it. That means it was upward exposed. So if we look at it from the beginning of the basic block, we see that expression as being definitely evaluated in that block before any of the operands were redefined. That's why it was upward exposed. So that is one piece of or one group of expressions will become anticipatable. Second group is that it was anticipatable at the end of that basic block, ant out set, you can see here. And it is not killed within that particular block. So it remains anticipatable. In other words, the path, if you look through the basic block, is simply and if at the beginning of the basic block itself, we know that along that path, which is now through the basic block, and all other paths which were at the end of that basic block, if they are merged, because of that, the expression remains anticipatable because it wasn't really killed. Along all the paths, the expression is still being evaluated without meeting any redefinition of operands or exit condition. So that's the anticipatability, or in the backward sense, how you propagate it through the basic block, that it is not killed, and it was anticipated at the end of the basic block. Now going to the again further backward in terms of predecessor of a given basic block, that's when it is anticipatable from the successors, only if it was anticipatable in each one of the successors. If it was not anticipated in one of the successors, it will not be anticipated in the predecessor's output. Why? Because if we go to that successor along which we did not have it anticipatable, we could find, of course, a path which did not have a evaluation of this expression, and therefore just by adding the edge between the predecessor and the current basic block, we haven't changed anything as far as the anticipatability is concerned. So that's why, in short, for an expression to be anticipatable at a given point, it must be anticipatable in each one of the successors block input sets. Okay, these two are very clear. And these are really fundamental to the understanding of why we are doing the formulation of PRE like this. So in short, if we come to a point of non-availability here, that basically means at least there is one path along which we don't have x plus y as evaluation in our hand because it was never ever evaluated. Or the other possibility is it was evaluated, but after that evaluation point, x or y has changed, and therefore the value is not exactly the right one. Both conditions are captured in the availability, non-availability definition that we have, and we really don't distinguish between the two because we need to cover it in either case. And the way we'll cover it is, of course, try and go to a place just following the non-availability edges. So maybe because the non-availability is because of, as I said, x or y being changed, then we'll stop right before, right after that particular point and place the new x plus y, just like the stopping condition we looked at did. So that's how we'll take care of non-availability because of the operand value changes. We'll place it on the edge right outside of that basic block and regenerate the value of expression there, and that will become available again because now it's with regard to the new values which had changed. Take the second condition that it was never ever evaluated. So then what will we do? We will keep going up and up and up. And this will not be the stopping condition that x or y has changed. But the stopping condition is, hey, now you're getting into a particular path on which x plus y was not anticipated. And so if you go above this point, anyway, it doesn't matter. Even if you just stop at this basic block or go to its predecessors or their predecessor, it doesn't matter. Because there is a path which is going to finally go through this basic block. It exists there. And if the control takes place and execution takes place in that way, then you are to have a superfluous expression, and that's why you stop there. So these are the reasons, and if it was not available, that is never ever evaluated on one side of stoppage and the other side, then it nicely places those expressions over there and provides their coverage. That's the whole intention of trying to provide the coverage in this particular way by completely exposing the redundancy. So now let us look at these conditions which I mentioned, earliestness, which I just formalized. So you can see that it's an edge condition. So we stop at a particular edge, which I showed earlier in this little sketch which I drew, on an edge ij, provided this is anticipatable in J block, okay, is not available at the output of I. So I is the predecessor block, J is the successor block here, okay, and it is not available at the output of I. It is anticipatable in J, which is the successor block, and which is either killed in the I block, that means we cannot move above that, or if I put it at the outskirts of I block, it is not anticipatable. So that you can see is the nice composite condition which defines the earliestness. So and that's what we had sketched out sometime back, which is the condition for where that particular block is we want to kind of place over here in terms of let me just go back to the whiteboard here and show you that. Okay, so here is that block. Here is another block here. This is my J block. This is my I block. And here is the edge which I was talking about, in which I'm doing the earliest placement. Now, there are two cases here. One is this case. So first of all, this is an edge of non-availability. Okay, so you can check that we are only going along those edges. And here is an edge of non-availability. So we select that only for coverage. And then we call this as the earliest if this is anticipatable here. So this is anticipatable here by this check mark in J. And it is not anticipatable, either not anticipatable in I, which because of this edge. So this is not anticipatable here. That's one reason for it. And the second reason for it could be that, forget about this edge for now. It is not possible to move above this particular point because of X redefinition. So it is not available here. That's the first important precondition. It is anticipatable in the successor. That is another condition. Those two are the conditions. So it is anticipatable in J. It is not available in IJ. Those two are the preconditions. And then the other two conditions is one of the two. We can't go above this I because either there's a redefinition, which means that if we go above I, we'll have a different value of this expression. And that will not really be sufficient for the availability side. Or this is not true. This X is not there at all, no redefinition. But if we go anywhere in I or above, we have the problem of this not being anticipatable in I, which means that it was anticipatable on J side. It is not anticipatable in I, which means that along this path, this never evaluated. And therefore, if I place X plus Y here, then you can see that it will go in this path and it will be superfluous. And that basically defines the earliest edges. Any questions? And as I said, by placing this expression over here, and let's take this condition, that's the reason why we are not able to rise above I, but really speaking, it could be that this X plus Y was in fact available here. So it is available here, not available here. And that's why it is not available in I and it's not available here. And by placing it here of non-availability that the earliest place, we haven't completely eliminated redundancy because you are going to face this problem of coming through this one and coming here, and now this is available here and this is placed here, and that's partially redundant. But it is inevitable because there is no other way to solve this problem. So it will leave some small partial redundancy intact because it is met with this condition of anticipatability. It cannot violate the condition of anticipatability. And so the idea there is to live with a little bit of partial redundancy. Okay. It is inevitable. There is no other solution based on that. Any questions? There aren't any, then we will go to our okay. So now let's go to the um, the lazy code motion formulation here. And this is simple. What we are trying to do here is push this expression down as much as possible, where and the stopping points are defining these predicates in terms of later predicates. So the way it starts is we have this earliest defined.
Sorry, Professor, just to check real quick. I'm not receiving slides right now. Are other people receiving slides?
Is everybody
So I
receiving
see your,
slides?
No, I'm not receiving the slides. I can see your download screen. Professor, I don't think you have like reset it after you switch back to the slides.
Let me just, I don't know what is going on. Let's do this again. How about now?
Yeah, it looks
okay.
good now.
Yeah.
Okay.
I can see it now. All right. Thank you.
Thanks for, yeah. Because here it was showing me I'm sharing it. I don't know what was going wrong. Okay, so we are at the now at the later point. In other words, we want to kind of sync these expressions from the initial points of coverage. As I said, we could have simply stopped here and that would take care of the partial redundancy. But obviously it would have placed very long evaluation paths along which we must hold the expressions, and that will lead to register pressures and all these bad stuff. So what's the idea? Idea is to push it down as much as possible till we don't re-enter the path of partial redundancy or availability. And that is done as follows. So what we do is we have these later edges ij initialized first of all based on the earliest ij edges. So that's where the later edge starts. And what we do is we say that we can sync it inside a basic block j, which is the successor of I again, provided we can sync it along all incoming edges to j. So if it is later along all paths, we can sync it. If it is not later along some path, we cannot, we must hold it right there in the later in ij. Why would we not be able to sync in terms of the all edges which are coming in into the path? Because it is possible that the earliest predicate on one side of the house is set to true because of non-availability and all other criterion being met. And on the other side, it is set to false because the expression was in fact available. As you see, that is the starting point of analysis to cover it along the non-available edge. So again, let me switch to this our whiteboard here. Here is the block. So earliest here is set to true. and earliest here is set to false. Why would that happen? Because this is available along this particular side, and this is not available, and it meets the condition for this earliest. Now you can see that the later in um, started here by setting those edges to this. So this later in started edges here, and it set the corresponding predicates. This is my J, this is my I block, and it started doing this. The question is whether we can sync it to this particular point, which I marked in X. The answer that is, it is intersection. Unless it is later in on both sides, which means it is set at the earliest on both sides, you cannot sync it. If it is not set to the earliest on left side, but it's set to earliest on right side, the intersection gives you false. And what it means is you cannot sync it below this particular point. And that is correct, because if you sync in, you are coming in the path of availability. Is that clear? Okay. So if both are set, let's take that example now, that both are set on earliest side, then we'll sync it in this block, because we'll take the intersection of the later in edges here. Let's say we are not meeting any evaluation point of this expression here, x plus y, within this block. So there is no need for its coverage along this path. So then why cover it at the beginning of the block? We might cover it, we might as well cover it towards the end. So that means the syncing through the block is enabled here in the absence of any evaluation. And so it is basically just like when we don't have any kill, we just pass the expression through. And in this particular case, if there is no x plus y sitting in the block, means there is no reason for it in the block. We'll simply sync it, and we'll go toward the end, and we'll keep doing that till we again see that it is available along one path, and it is later in along another path. So this later in would basically be true here, and this later in will be false because of availability. And now you can see that if you take this intersection, this will become false. And so the right point of placement here is when the letter in at the beginning of the block is false, and letter in along the incoming edges is true. So remember that, okay? So the point of coverage here is this. The letter in along one of the incoming edges is true, and whereas the letter in at the beginning of the block is false. And that's the point where the availability meets the later in. That is one coverage point which we'll go ahead and place it. So first we'll compute all these later ins, find out this condition of availability and later in at the latest point where it's setting the later in true as false, whereas the later in is true, and we'll try to cover it at that point. Okay, so so let me come to the now can you see my original slides?
Yes, they're good.
Okay, so you can see that we are computing these later in predicates, first starting with later in edge predicates, same as earliest predicates, and then syncing them at the beginning of the blocks by computing their intersections. So if all later ins are true, which means that we can push this expression down for sure without coming in the path of availability, we will go ahead and set that predicate true later in J. However, if on the one edge letter in ij was false, then obviously letter in j will become false. Note that. Now, once we are inside a block, what we do is we see if there is any evaluation of that particular expression. And if it is not there, then we are simply sending this evaluation further downhill towards the end of that block. So how do we do that? We're syncing it through I block. You can see that there is no evaluation of the expression in I block. So we're syncing it straight to its end. And so therefore, all the later in edges, which are our exit edges from I to corresponding J's, they will become true. That means that the expression can flow now and should be evaluated along all the outbound edges at the end of I. So we'll basically keep doing this, and finally we'll be at this particular conditions. As I said, next is the insertion condition, which we'll evaluate. How do we do that? We know that letter in is true along at least one edge, ij, and letter in j is not true, which basically also means that letter in is not true along one of the incoming edges to j, which is the condition which I had shown earlier because of availability. And so therefore we cannot be any later than this particular edge, and we must cover it along ij, along which this is the latest point on which we must cover it, because if we cover it any later, we'll be in the path of availability, and so therefore we insert this expression, x plus y is evaluation, and ij edge. Okay. Now let us find out what is the deletion point of a particular expression means. So deletion point of an expression is that obviously if the expression is upward exposed, so there is an evaluation of an expression in a block, okay, in a block K, and letter in to K is false. What it means is it is covered at the beginning of that block. Why this false predicate? Because you can see that the first condition, the insert condition, would have taken care of it. It was partially available. It was available along one edge. It was not available along another edge. That led to that letter in K being false. Okay, because it was letter in predecessor of K along one edge to be true. That means it needed a coverage there, but it was false along the other edge because it was available, and therefore the intersection, which is later in K, was false. And it is exactly the case which is taken care by the insert predicate there. And in such case, it would have inserted it along the ij edge, along which it needed to be inserted without coming in the path of availability. And therefore, it has made now whatever is inside this K, which is upward exposed expression K, as redundant. So when both these conditions are met, that expression K, which is upward exposed in block K, is deleted. Okay, I hope this is clear why this deletion is a good idea. Now let us consider the other case when letter in K was in fact false. Okay, so remember when letter in K was false, and if the expression was upward exposed, okay, we deleted it. Okay, but what if the letter in K, now the second condition is true, that the letter in K expression was true, and the upward exposed expression is also true. So you can say in this particular case, the deletion predicate is false and the expression is not deleted. Why? So let me explain that again, going to our um, uh, whiteboard, and that's the last thing we'll be doing today. So here is an expression, x plus y. That's why it is upward exposed here. Okay, and here is the case wherein letter in here is true, letter in here is true. Okay, and this leads to the letter in here being true because it's an intersection operator. What it is showing you is on the right hand side, the expression was not available, and this was an earliest edge, and this was propagated through it, and there was a need for coverage for this expression. Okay, so this means that need for coverage is expressed here and on the left hand side both. And that led to this expression, the need for coverage, resulting in letter in true in this particular part. So now let us look at letter in true, letter in, let's call this block as J, or K rather, which is consistent with the terminology. So letter in K, in this particular case, again note, it's true, and its negation is false, of course. Okay, and that intersected with the upward exposed expression. So the x plus y is an upward exposed expression. So that is also, so this side is true and it's intersected with a false. Okay, because letter in is true, its intersection, its negation, which is what we are looking at, negation of letter in is basically false. What it means is there was a need for coverage here for the expression from all sides, which means that it was never available on any of these sides, and this x plus y is sitting there, and when we take this intersection it is false, and therefore the delete predicate here will remain false, and this will not be deleted. This will remain intact. So what it means is this, that the topmost level evaluations of expressions, again from the root of the program coming along to this, along which they are not available along any paths, they are the anchor points where the redundancy really starts. They are not redundant because nothing before that has evaluated x plus y along any path, and those are protected by this framework. They are not deleted. However, if the other case, if they are partially available along one path and the placement along the other path covers them, then they are partially redundant, which is the other case of this was what I will modify here is it was not available along this particular path. So letter in was true here. The letter in was false there because of availability being true, and so this will become false. And in such cases, you can see that negation of letter in will become true, and the upward exposedness is over there, and which basically means that we will be covering it by placement here through the insert, and we'll be deleting it over here. Okay, so that's the second case. So in short, whenever it is a topmost level expression which is uncovered, the predicates handle it without deleting it. However, if it is covered along one edge and not covered along the other edge, they will do the placement along the other edge, cover it first, and then that will lead to the predicate letter in becoming false, and they will delete that eventually because of the negation of letter in and the upward exposedness being together, resulting delete predicate being true, and that's how they will get rid of it. Okay, so So that's partial redundancy. And no, it's a little complicated topic. Hopefully some of these explanations, detailed explanations, along with its examples and the one which we have given to you lead to exercising these concepts well. Are there any quick questions, or we can head to the office hours and we'll stop here for today? All right. Those of you have any questions, do come to office hours. Somebody might ask some question and it might help you to clarify your things. So I'll stop here and we'll go to office hours. See you then.